Chapter 8 is Earth Systems and Resources. It's things that we're familiar with: soil, rocks, plate tectonics, earthquakes. But I'm going to try to point out the 8 relevant topics to you. The chapter starts off talking about hybrid electric vehicles and whether or not they're environmentally friendly. They're all electric vehicles or hybrid electric vehicles that use part gas, part electric. And they're great because they allow us to use less fossil fuels. But what we don't think of is that they need some scarce metals. And in order to obtain these scarce metals, we need to mine. And mining involves disrupting large areas of land. So with every benefit, there's also another side to the story that we have to take into consideration when we're considering environmental impact. Earth resources were determined when the planet was formed. Early Earth was a hot molten sphere. Debris from the formation of the sun bombarded it, and then that molten material cooled. The heavier elements sank towards the Earth's center, and the lighter elements, like silica, floated towards the surface. Although occasionally we can have an asteroid hit the Earth, for the most part, elemental composition is stabilized, meaning we're not getting any more new elements. These elements and minerals are distributed unevenly around the Earth. Things like silicon dioxide are readily available worldwide on beaches and shallow marine areas. But things like diamonds are localized because they need intense pressure found in relatively few isolated locations. And this causes economic and political conflicts. Earth's elements settled into place based on their mass, and so the planet is characterized by distinct vertical zonation. The core, 3,000 kilometers below Earth's surface, is a dense mass, mostly nickel, some iron. The inner core is solid. The outer core is liquid. And above the core is the mantle with the molten rock or magma. And magma slowly circulates in convection shells, and that's going to become important later on. So if we superimpose a cross-section of the Earth over the United States just for size relevance, we sort of know this inner core, there's our outer core, there's our mantle, the things that we're familiar with. But here's some of these environmental science words: this asthenosphere and lithosphere, and then the crust. Very, very thin layers that are very significant to us. This asthenosphere is located in the outer part of the mantle. It's semi-molten, a ductile, sort of flexible rock. The lithosphere is the brittle outermost layer. It's from the Greek word lithos, which means rock. It's about 60 miles thick. It includes the solid upper mantle as well as the crust, and the crust is that chemically distinct outermost layer of the lithosphere. It's made of several large and numerous smaller plates. Over the crust is a thin layer of soil that allows life to exist. It's important to recognize that these regions overlap, and the lowest part of the lithosphere is also the uppermost portion of the mantle. Earth is very hot at the center. It's thought to result in the radioactive decay of various isotopes of elements, potassium and uranium. It produces hot spots, and this is where molten material from the mantle can reach the lithosphere. It's an important component of the Earth's dynamics. If we start looking at some of the Earth's layers, we think about 1912, a German meteorologist named Alfred Wegener. He proposed that the world's continents had once been joined in a single landmass called Pangaea. Prior, we believed that everything was fixed in place, and fossil evidence has shown otherwise. I'll show you a diagram in a couple slides that reinforces this. But since we know that this lithosphere is broken into plates, it's an important factor in a lot of things that happen on the Earth. Looking at convection and hot spots, the Earth is very hot at the center, and this causes plumes of hot magma to well upward into the mantle. It produces hot spots where this molten material can reach the lithosphere, that can make its way up. There's also these convection cells in the mantle, and this is similar to the convection currents that we studied in the atmosphere just in the last chapter. So here's this theory of plate tectonics. So Alfred Wegener proposed this idea of Pangaea and said, hey, look, it sort of looks like these continents fit together, and also there's fossils of animals that shouldn't really have had contact with each other, on opposite continents. Scientists said no way, and in their ability to try to disprove it, they actually found more evidence to support it. So they had to support his Pangea idea. The tectonic cycle is the sum of these processes that break up and break down the lithosphere. So here's these tectonic plates. So we know that the lithosphere is broken into plates. We know there's oceanic plates and continental plates. Oceanic plates lie primarily beneath the oceans, and they are dense and they're rich in iron. Continental plates are under land masses, and they are less dense. There's more silicon dioxide, more sand than iron, and therefore they're usually lighter and rise above the oceanic plate. This has become important when we see how these plates interact. The movement is driven by those convection cells that I pointed out in the last slide, where we have that magma convecting, and it's going to help influence how these plates move. As movements occur, continents slowly drift, and the seafloor is spreading. So when oceanic plates move apart, rising magma creates new oceanic crust on the seafloor between those two plates. Subduction is the process of one plate moving under another. And the heavier plates slide underneath the lighter plates. So you can see there's areas where plates are spreading apart. But if there's areas where plates are spreading apart, then there must also be areas where plates are moving together. So we have a spreading zone and we have a subduction zone. Plates move slowly, mostly like 36 millimeters per year. So the plates underlying the Atlantic Ocean, if we put this in perspective, have spread apart and come together twice over the past 500 million years, causing Europe and Africa to collide with North and South America and separate from them again. And that's happened twice. So that sort of puts things in perspective as to how long the Earth has been here, and then how slowly these plates are moving, but then how dramatic that cause is. If we look at a geographic time scale here, as the continents drift over the Earth's surface, scientists use this fossil record to determine how organisms have adapted over time. So it's sort of what I was talking about before, how plates have spread apart and come back together and over 500 million years twice. And then we can use these fossil records to sort of follow both geographically and geologically. Consequences of plate movement. So what's going to happen when plates move? Volcanoes, as a plate moves over a hot spot, rising magma can form a volcano. So we can see how our Hawaiian Islands have formed. This is the oldest Hawaiian island, formed 4.89 million years ago. And as this plate has moved, and we can follow the position of the hot spot, and this is the new island that is forming over the current location of the hot spot. So this is our oldest island of Kauai, and this is our youngest island, the island of Hawaii. So here we get to types of plate contact. So these are the ways that these oceanic and continental plates can meet each other. We can have divergent plate boundaries. So plates are moving apart from one another. And like we said, if we have divergent, we have convergent as well. Divergent plate boundaries is important because it brings important elements, copper, lead, silver, to the surface of the Earth. It allows spaces for this magma to escape. Convergent plate boundaries are when plates move towards one another and collide. When oceanic plates and continental plates, or two continental plates, meet each other. When we're converging, one of them has to go below the other one. And then when we have transform fault boundaries, these are the ones that slide, move sideways past each other. They sort of end up getting stuck, and then they'll slide a whole lot. And that's what's going to give us our earthquake. So I just spoke of these three different boundaries, and these transform fault boundaries are the ones that are primarily responsible for earthquakes. A fault is a fracture in a rock across which there's movement due to plates moving. So we have fault zones. Earthquakes occur when the rocks in the lithosphere rupture unexpectedly and move along a fault. Essentially, they get stuck, and then when they get unstuck, they move rapidly and can cause great destruction. If we look at the San Andreas Fault, This is the one that we are probably the most familiar with. It is most of the coast of California and near Los Angeles there. Fault zones are called areas of seismic activity. The epicenter is the term for the exact point on the surface of the earth directly above where that rock ruptures. The Richter scale is how we measure the severity of an earthquake. It increases by a factor of 10. It's like a pH scale. So an earthquake of a magnitude of 2 compared to an earthquake of a magnitude of 3, the magnitude of 3 is 10 times worse than the magnitude of 2. Both earthquakes and volcanoes are disruptive to human life. The earthquake in Haiti in 2010 cost 200,000 people their lives. That was when that occurred. Now moving on to rocks. The rock cycle is the slowest of all of the cycles on Earth, but it is truly a cycle. It's the constant formation and destruction of rocks. So we form new rocks from magma, but we also have rocks that get destroyed through weathering. So the formation of rock occurs when magma from the Earth's interior reaches the surface, cools, and hardens. Weathering then occurs where rock masses are broken up, moved, and deposited. The different types of rocks we have are igneous rocks. They are the ones that form directly from magma. They are classified by chemical composition, such as basaltic or granite. Basaltic is a dark-colored rock. It's high in iron, magnesium, and calcium. It's dominant in the crust of oceanic plates, which is why they are more dense. Granite is a lighter-colored rock. It's higher in feldspar or mica or quartz. It contains more silicon and aluminum, potassium, and it's more in continental plates. Mode of formation can be intrusive or extrusive. Intrusive igneous forms within the earth as the magma cools, whereas extrusive is when magma cools above the earth, like a volcano that ejects magma will do this. Sedimentary rocks form when sediments such as mud and sands or gravels are compressed over overlying sediments. It occurs over long periods of time. These are where we typically find our fossil records. And metamorphic rocks form when sedimentary, igneous, or other metamorphic rocks are subjected to high temperatures and pressures. They cause physical and chemical changes in the rocks, so stones such as slate and marble, anthracite, which is coal. They're often used by human civilization because they are very strong. Fractures are cracks that occur when rocks cool. It can occur in any kind of rock. Water will move through these fractures and dissolve valuable minerals and precipitate them out and form deposits, so veins. So important deposits of gold and silver ores are formed this way when there's fractures in rocks, and then water is allowed to move those minerals through. Weathering and erosion. Weathering is when rocks are exposed to air, water, certain chemicals, or biological agents that degrade the rock. Physical processes, chemical processes, and erosion. Physical weathering is the mechanics, the breakdown of rocks and minerals caused by weather, caused by wind, water, things that can physically break apart rocks, which is different from chemical weathering. That's the breakdown of rocks and minerals by chemical reaction. So it releases essential nutrients from the rocks. This is when we have acid rain or something that is basic that comes in contact with rocks. Physical weathering can also be occurred by biological agents, things like plant roots working their way through rocks, like the picture of the tree there. And chemical weathering is significant because it releases those nutrients that now plants and other organisms can use. Lichens secrete acid to help break down rock. Carbonic acid will break down limestone. Erosion is the physical removal of rock fragments from a landscape or ecosystem. Wind, water, ice, transport, living organisms, natural processes, human-caused, and then deposition is the accumulation or depositing of eroded material, such as sediment, rock, or fragments of soil. That hits most of our terms for this part of the unit, and then the next video will focus on soil and mining.